SwayamPrabha. Digital India. Educated India.
So far we have seen the analysis of ER and MR fluid flow in a rectangular passage. Now today we will see how the formulation looks if we consider an annular passage. So an annular passage looks like this. So there is two concentric cylindrical domains. The inner cylinder is a solid cylinder, outer cylinder is a hollow cylinder. So the inner cylinder is between inside the outer cylinder. So when the inner cylinder moves or remains fixed, when the inner cylinder moves it gives rise to a shear mode. When the inner cylinder and the outer cylinder is fixed, that is a flow mode. Now the fluid is flowing in this region. So between the inner cylinder and outer cylinder, that annular region is filled with the fluid. So when both the cylinders are fixed and the fluid is driven by a pressure, it is a valve mode or flow mode. When the inner cylinder is moving and that is causing the fluid flow, that is a shear mode. So we will analyze a shear mode here. So and we are doing a shear mode analysis. Now to do this, again let us take a small fluid element. So we are taking a small fluid element here, which looks like this. And we have the pressure P, and pressure is increased to P plus del P by del x into dx. Now we are taking a fluid an element in this region of length delta x, and we are taking a cross sectional view of the delta x region. So from outside it looks like this curved, but if I take a cross section through the center it looks like this, and we are analyzing the flow there. Now this is our shear at the top delta r by dr. Now here our consideration is this is at the center and the distance from the center to the top or bottom is r, and this dimension is our x, and the velocity along x direction is called u. So here we have tau. So this is our solid cylinder inside, this is the outer boundary of the outer cylinder, the top boundary of the outer cylinder, the bottom boundary of the outer cylinder, and this is our annular region. Now we are studying only one annular region, and that is sufficient for understanding the flow behavior. Now here we need to find out the mass of fluid element. So mass of the fluid here is 2 pi r dr dx rho, where rho is the fluid density. So rho is fluid density. Now 2 pi r dr dx. So 2 pi, so this is our, as we know, this is our dr. So this dimension is dr, and if I multiply this dr by 2 pi r, that gives me the total cross sectional area of the annular region considering the 360-degree revolution. And then if I do 2 pi r dr dx, that gives me the volume of the fluid element. So that means the volume of the fluid element throughout this considering a length delta x. So that is the volume of the fluid element. And then we have, after having the expression of the mass of the fluid, we can now write the equation of motion. So the force balance, so the total force is equal to the mass into acceleration. If we do that, then finally the equation that we get is minus, and this quantity we may write as dm. So minus of dm multiplied by del u by del t plus 2 pi r dr plus tau plus del tau by del r dr 2 pi multiplied by r plus dr dx multiplied by tau 2 pi r dx, then we have minus p plus del p by del x into dx into 2 pi r is equal to 2 pi r dr is equal to 0. So, we are finding out the total force due to this pressure here minus the total force due to this pressure here. The total force due to this pressure is this pressure multiplied by this thickness, and then we multiply that by 2 pi r. Similarly, we find out the total pressure here due to the total force due to this pressure. We find out the total shear stress, total force due to this shear stress, and that is this shear stress multiplied by this length, and then we multiplied by the periphery 2 pi r. And similarly, we find out the total force due to this stress, and that net unbalance is equated with mass into acceleration. And after doing that, finally the equation simplifies to minus rho del u by del t plus tau into tau by r plus del tau by del r minus del p by del x. And then we assume that the flow is quasi steady. So, del u by del t is 0, and that gives me del t by del r plus tau by r is equal to del p by del x. So, this was the governing differential equation, and that is valid for both shear mode and the valve mode, valid for both shear and valve mode or other mode. Now, only thing is that when we are in the shear mode, del p by del x is 0 because it is not pressure driven. So, in shear mode we have del tau by del r plus tau by r equal to 0. Okay, now first we will do the solution for 0 applied field. Now, in the 0 applied field, we know that the fluid constitutive relation is tau is equal to mu multiplied by del u by del r, and if that is so, if I put this in this equation, then the governing differential equation becomes mu into del 2 u by del r2 plus mu by r multiplied by del u by del r equal to 0, and this can be written as del by del r of r multiplied by del u by del r, because if I take mu out, then del 2 u by del r2 plus 1 by r into del u by del r is our derivative of r into del u by del r with respect to r. Because if I take my mu out and then this if I put this r here, so it becomes r into del 2 u by del r2 plus del u by del r, and that is equal to the derivative of r into del u by del r with respect to r. Now, I can integrate this equation, and integrating we get u as a function of r as a natural log of r plus b. So, where a and b are the constants, and then we can apply the boundary conditions. So, the boundary conditions are at r is equal to r I, we have velocity is equal to u 0. So, that is the velocity at which the inner cylinder is moving, and r is equal to r o r 0, that means outer radius, there the velocity is 0. Because if I go back to the diagram, if I say that the inner radius is r I and the outer radius is r o, and we say that the inner cylinder is moving with a velocity u 0 and the outer cylinder is fixed. So, at inner cylinder because of the no slip condition, the boundary condition is u is equal to u 0 here, and here because of the no slip condition the boundary condition is u equal to 0. Now, after putting the boundary conditions, I can evaluate the constants. So, these are now a b. So, a is equal to u 0 divided by the natural log of r y by r 0, r I by r 0, and this gives me that b is equal to minus of u 0 natural log of r 0 divided by natural log of r I by r 0. So, finally, my u as a function of r becomes u 0 divided by natural log of r I by r 0 multiplied by natural log of r by r 0. Now, if this is so, then the shear stress tau is equal to mu into del u by del r, and that becomes minus mu u into u 0 r into natural log of r 0 by r I. Now, we can find out the total force F 0. So, the total force F 0 is the force at the surface of the inner cylinder, and that force is, to evaluate the force I have to evaluate the shear stress at r is equal to r I, and then multiplied by just 2 pi r I into length. So, here we are considering that the length of the cylinder is L. So, if this is my fluid element dx, and if I say that this dx is a part of the cylinder. So, the length of the cylinder is suppose L. So, if I do a cross sectional view here, that becomes our total L. So, this total L, this dx is, this is a just, this is just this part. So, that gives me that the force F 0 is 2 pi r I multiplied by r into tau evaluated at r I, and that gives me 2 pi into L into mu into u 0 divided by the natural log of r 0 by r I. And then with this we can find out the expression for the active damping coefficient, the damping coefficient. So, the damping coefficient becomes F 0 is equal to C equivalent into u 0, that is the force, and the damping coefficient is F 0 divided by u 0, and finally the expression is capital gamma into u, where capital gamma is 2 pi L divided by natural log of r 0 by r I. So, that was for the inactive case when I have 0 applied field. So, yield stress is 0. Now, we will consider a non-zero applied field. Now, in the non-zero applied field, we have the fluid constitutive relation is tau I into, we know the sign of gamma dot plus mu into gamma dot. So, when gamma dot is negative, it is minus tau, when gamma dot is positive, it is plus tau I. So, it is tau equal to tau I plus mu into gamma dot when gamma dot is positive, and minus tau I plus mu into gamma dot when gamma dot is negative. Now, if I put this constitutive relation, then my governing differential equation becomes this. Is equal to tau I by r, and again this can be written as partial of r into del u by del r with respect to r is equal to tau I by r, and then finally on being integrated, this gives me u as a function of r as tau I divided by mu into r plus c natural log of r plus d, and then we can evaluate the constants applying the same boundary conditions, that at u is equal to r I mean at r is equal to r I, u is u 0, and at r is equal to r O outer boundary, u is 0. So, these boundary conditions gives me that applying the boundary conditions, applying the above boundary conditions, we get C equal to minus 1 by natural log of R O by R I multiplied by u 0 plus tau y divided by mu multiplied by R outer minus R inner, and then we have d is equal to u 0 divided by natural log of R 0 by R I plus tau y by mu, and this is multiplied with minus R 0 plus R minus R I divided by natural log of R 0 by R I. And then after putting that in the expression of u, we get u as a function of R as minus tau y by mu multiplied by R O minus R plus mu 0 plus tau y by mu multiplied by R O minus R I divided by natural log of R outer by R inner multiplied by natural log of R 0 by R. Now, from here we can find out tau as a function of R as minus of mu divided by R multiplied by natural log of R 0 by R I into u 0 plus tau y by mu multiplied by R O minus R I, and that finally can be written as minus mu into u 0 divided by R into natural log of R 0 by R I into 1 plus B I, and where we know that B I is the Bingham number. So, B I is Bingham number, and that Bingham number is the ratio of the yield stress by the viscous stress. So, this is tau y multiplied by d by mu u 0. So, tau y is the yield stress, and mu u 0 by d also has a dimension of stress, and that is the viscous stress. So, yield stress by viscous stress is our B I, a Bingham number, and that is how we express our shear stress tau. And then from here again we can find out the force F 0 as 2 pi R I multiplied by length into tau at R I, and that gives me this as mu into 1 plus B I into capital gamma u 0, and we have already defined capital gamma. So, this quantity helps us finding out the active damping coefficient, and we can write that as F 0 by u 0, and that we get as mu into 1 plus B I into capital gamma, and then if we do C equivalent of active case by the inactive case, we get this as 1 plus B I, because mu capital gamma was C equivalent 0, I mean C equivalent for the inactive case. So, that is how we analyze it for the annular passage. So, we can see that the method is same, only due to the geometry we have to be careful. So, instead of working on x and y, we are working in x and r, and accordingly everything falls into place. Now, this same procedure can be extended to the analysis of the flow mode or the valve mode. Now, in the next week we will again look into flow mode analysis and valve mode analysis, considering again rectangular case, but using different constitutive relations. So, this brings us to the end of this lecture and this week. Thank you.